Okay, so the whole semester, really, from the first day, this is the problem that I think you should be able to solve by the end of the semester.
Is this meant to be screen shared?
Yes, is it not being screen share?
Maybe not.
Now I have a new share here. I think it's being screen share. Let me pause it. That will. Okay, so is no sharing. Let's see. Let's double check this stuff. Okay, so this is the example that I think you should be able to do by the end of this class. So, all right, so basically is we have a wing box again, like always. Imagine that everything you model here is like you're doing a wing, okay, a wing, some type of wing box structure. All right, so imagine this end, like always, like if it was a wing clamped to the fuselage, so it's cantilevered as the assumption. Current system is going to start from this end. This is Y, X, oops, and Z. So over here, we're going to have areas of stiffeners. Let's say this one, you have one here, cell with another stiffener. Okay, and let's say across the cross section, there is a shear force dy. The total length L is 1,000 millimeters, and the number over here goes from 1, 2, 3, 4, 5, 6. Properties E equal to 69,000 tons per millimeter square. G equals, so this is for aluminum, 25,900 newtons per square. We know that the boom areas is B1 equal B3 equal B4 equal B6 equal to 650 millimeters square. B2 equal to B5 equal to 1,300 millimeters square, and Vy apply at shear center. Okay, I'm going to do another little small figure here. Give some more data, and then we're going to discuss the problem. 1, 2, 3, 4, 5, 6. The depth of the wing box is 250 millimeters. Section here is 250 millimeters. And this one here is 500 millimeters. And the thickness of every single panel is T equals to 2 millimeters. Okay, the question here is to determine the deformation at the free end. Okay, so this is a problem that is not new to you, no? Except for what we need to find is what the deformation instead of the shear force, but it's exactly the same thing. So what happened that they say that they mentioned this problem that the Vy force is applied to shear center. What does that imply? Anyone?
There's no moment.
Correct. So there's no moment. In this case, the moment is really the torque. So basically, this is just going to move up and down, and it's not going to be any twist, no? Yes? So if you want, let's write it down just to make sure. Okay, shear center. Vy at shear centers implies no twisting of the wind box. So basically, this would just be moving up and down. It doesn't change anything at the procedure, but okay, so we know that in order to find the deformation, we're going to use the Castigliano's theorem, which implies the use of strain energy. So remember that we broke the strain energy into different components due to axial, due to bending, due to torsion, and due to shear, no? In this case, this wind box will be subjected to what? What type of loads? We'd have axial energy or no? I see some people saying yes, some people saying no. I mean, we have, is it an axial force? Let me put it this way. No, okay. Now, is it a bending moment? Yes, no. Is it a torque? It's not torque because we say it's applied to the shear center. Will we have shears? Yes, okay. So basically, we could say in this case that the strain energy, in this case, which we use the letter U, will be equal to what? To the strain energy due to bending, which is 1/2 m squared over EI along the length dz, plus the 1/2 0 to L, 0 to L of the shear. I derived these expressions before, but Q squared over GT ds, and here will be dz. So again, this is the strain energy. Sorry.
Use the thing a little bit.
In?
Yeah, a little bit.
Yeah, it's fine. Doesn't you know then when I move out of the. Is that better? Okay. So this will be the strain energy due to bending. So bending. And shear. Okay, so we know that the deformation is obtained by taking the partial derivative of this one with the force applied at a given point. This becomes what? 0 to L of partial of M I over EI partial MI partial Q sub I dz plus integral 0 to L of partial Q. Okay, so done differently, it doesn't matter. Partial Q sub I over GT. Oops, ds. Yeah, that's correct. Okay, so again, this will be, I think will be redundant, but this is the formation. Due to bending, and this will be the formation due to shear. Okay, if you have any questions, stop me on the way, okay? All right. So we're going to do one term at a time. First one will be fast, so one will be a bit longer. So the formation. First, the formation. Due to bending. Okay, so that will be the expression Q sub I equal integral 0 to L of M sub I over EI partial of MI over partial Q sub I. Okay, so over here, what do we need to determine? We need to determine the moment. So if I do a figure, a sideways figure, in this problem, it's pretty easy. What do we have? We have the Vim box, which is subjected to a force Vy over here at a distance L. Okay, I'm going to skip a little bit of a. I mean, if you want me to give details, let me know, okay? Otherwise, I'm going to skip it, okay? Just to give too many details. What is the shape of the bending moment? What is the moment at the tip? What should be the moments at the end? Zero. And what should it be at the root where this is applied? Correct. So it will be basically the straight line where here is 0 and here the M max is Vy times L, no? Okay. So really the moment equation is a straight line that is equal to what? What is the value of the value at the root should be Vy times L, no? And at Z equal L, it should be 0. So can I write the moment equation at Vy equal to Z minus L? If you need me to show you how to do it, I can do it, okay? But if it's okay, I'll do it this way. So that way at L, what would be the moment? L minus L, 0, no? And at Z equals 0 will be Vy times L. Maybe I should have put L minus positive. It's good. Or if you want, if you can erect, put L minus Z, so we have the positive value. Doesn't change anything, but that way as Z equals 0 is Vy times L, and then one it will be negative. No? Should be the same thing. Okay, and now, since it's pure bending over here, okay? Up and down. So that means that any one of these points is gonna have the same deformation, correct? Yes, moving up and down, up and down. So for simplicity over here, let's say we can select Q sub I to be equal to what? Do we need to apply a fictitious force or can we just take Vy? Since it's gonna be the same everywhere. You take this one to be equal to Vy. Yes? Okay, it's at the tip, no? Yeah, and all the points are gonna move the same, so. All right, so let's call maybe this equation here Roman 1, and let's write over here substituting into 1, what do we have? Q sub, let's say 1 will be equal integral 0 to L of M. So let me put the general equation would be M over EI partial M partial V of Y dz. So this will be equal to what? Integral 0 to L. M is Vy of L minus Z divided by EI times partial of M with respect to Vy will be equal to what? What will be this term? This term will be equal to what? L minus Z. So we're over here times L minus Z. Easy. Okay, so we simplify a little bit this. This gives you Q sub 1 will be equal to what? Vy over EI. If you want, I can keep everything in integral. EI of L minus Z squared. Easy. Okay, so again, this will be expression I, which is deformation due to bending moment M. So due to bending. All right, so next is what? To find the deformation due to shear. So 2 deformation due to shear. Okay, so this one I'm going to call it Q sub 2. I'm just copying the same expression as before. Would be integral to 0 to L. You go across the cross section due to the shear flows will be Q sub it will be okay, Q sub I here, Q sub I times what the G divided by T partial of Q sub I partial Q sub I ds dz. Okay, where again we're going to do the same as before. We're going to say that relative force we're going to take dy, and what would be the Q sub I? The shear flows. So which shear flows will be the Q's? Will be so let's see the numbering. 1, 2, 3, 5, 6 will be all the different shear flows over here, no? So we need to determine all the different shear flows. So this is a problem that we have solved before. So first, is this statically determined or indeterminate? Statically indeterminate. So again, I'm just going to put it because it's like starting with you over here. So statically indeterminate. Because we have two cells. If we only had one, it will be statically determined, no? Okay. So basically, what is the procedure? So if you want to do here a little figure, I think the little figure should explain the procedure. Again, this will be like a review. What do we do with this? What do you do? So this is the Q bars, no? Q bars, if you want, this will become what? How many cuts do you need to do? 2. You see over here, mathematically, you can do the cuts anywhere you want, but if the force is coming on the y direction, I like to do it on this one because you know that in theory, what should be the members that should carry the loads on the vertical direction? Should also be the members on the vertical direction, no? Okay, so you can do the cut there, but I think you lose symmetry. You put it here, I think it's better. And then plus what do you need to do then the second step over here? We need to assume a internal shear flow, let's say Q sub 1, Q sub 2. Okay, so this is like a review. Okay, so now let's keep going. It's just routine. So what is the expression we're going to be using? Q sub S will be equal to minus Vy. Pretty sure remember that equation. Ixx summation of the E sub R, Y sub R. Yeah. Okay, so before we go, we start doing this. What about if we first find what is the Ixx? Okay, so you can see over here, the cross section is symmetric, no? Because if you look at the values, this value is equal to this one is equal to this one is equal to this one. So what does that mean? That we're gonna have an axe of symmetry along this line, no? Yeah. So let's see what was the numbering. 1, 2, 3, 6. We knew this one was 250. Okay, so the IXX will be equal to what? Summation of what? How do we do the B? Will be B sub R, Y sub R squared from 1 to 6. What are you gonna have over here? All right, I'll do it very quick. If you want B1, Y sub 1 squared plus B2, Y sub 2 squared plus B3, Y sub 3 squared plus B4, Y sub 4 squared plus B5, Y sub 5 squared plus B6, Y sub 6 squared. Where, what is Y1? What will you have? Y1, Y2, Y3 equal to what? 125, and then Y4, Y5, Y6 will be equal to what? Negative 125. And I did give you the values for B1, B3, B4, B6, B2, and B5, no, on the previous page. Okay, so if you do that calculation, I do it for you. I mean, is IXX is equal to 81.25 10 to the 6 millimeters to the 4. Okay, so maybe I'm going to start here and then I move to the next page. So let's see. Let me put the number. This is 1, 2, 3, 5, 6. Maybe that's the only one we need. Okay. So let's see. What do we know? If we start from 1, 2, what is Q12? 0. Okay. If I go around, what would be Q23? If you want, theoretically, it would be Q12 plus 1 would be 0, no? 0 will be 0. Okay. Then Q34 should be equal to what? Q23 minus the Vy over IXX of what? E3Y3. So this will give you 0 minus, let's say I leave it on the Vy. Looks like it's going to work better for the algebra. Divided by the 81.25 10 to the 6 times, what is the value for B3? B3 is 650. What is Y3? 125. And if you do the calculation, this should give you minus Vy over 1000. So the good thing about making the cuts on members that are not in the direction of the force is that if we follow our common sense, what should be the load in 4-5? 0. And in 5-6? So that will help us to check our answer, no? Okay. So next one, we go 3-4. Let's go to 4-5. So we get right here Q45 would be equal to Q34 minus Vy over Ixx times B4 times Y sub 4. So this is giving you, I'm gonna go here, it's giving you minus Vy over 1000 minus Vy over 81.25 10 to the 6. Then B4 is what? Same as B3, which is the 650. Okay. But now what is the difference? Y3, instead of being positive 125, is negative 125. So then what does that mean? That this term is going to be the opposite, and this one is going to be 0, no? It's completely the opposite than the one we did before. Here we had positive 125. Here we have negative 125. The rest is the same. So Q45 is equal to 0. Okay, now let's do the one that's a bit more complicated, Q25. Q25 would be equal to what? Would be equal to what? Q12, no? Plus Q23. Both are going in here, no? To 2, and now we go from 2 to 5. Minus Vy over Ixx times what? V2, Y2, correct. So we know these ones are 0 and 0. So this one here, maybe we can save some calculations. Basically, you see that B2 is basically twice the one we had before, no? Okay, so if before the simplification was given minus 1 over 1000, this should be equal to what? Minus 2 over 1000 Vy, no? Is that okay? I just do that. So this should give you that this is equal to minus 2 Vy over 1000. Okay, similarly, Q56 would be equal to what? Q25 plus Q45 minus Vy over Ixx. What? V5, Y5. Okay, so we can do the calculation, but I mean, we're going to check, but what should be the value if we are correct? Should be 0, no? So let's see what we have for Q25. Q25 is right here. We have minus 2 Vy over 2000. What is Q45? Is 0 minus Vy. I mean, this is again the B5 before it's symmetric. So, okay, minus, doesn't matter, that's 81.25, 10 to the 6. B5 is the one that it should be 1300 and minus 125, which basically is the negative sign of this one. So basically we get 0, okay? You can do the calculation, but we should get 0. Yes?
So it's supposed to be -2.
This term over here? Oh, yes, yes. 1000, correct. Thank you. Okay, so let's say we did 1, 2, 2, 3, 3, 4, 3, 4, 4, 5, 2, 5, 5, 6. We need to do now 6, 1. Q61 would be equal to Q56 minus Vy over Ixx is 6y6. Okay, and this is going to give us Vy over 1000. All right, so if you want, we can do a little figure here because I always like figure to summarize results. So basically we have here 0, 0, 0, 0. We know Q34 is equal to minus Vy over 1000. Q25 we say was equal to minus 2 Vy over 1000, and Q61 was equal to Vy over 1000. Okay, so now when we look at this, we did this part of the solution, no? We need to find the Q's. You find the Q's. Now we need to find this part here. We need to find Q sub 1 and Q sub 2, no? Okay. So what is the condition we're going to use for that? So what do we know? Vy applied at shear center What does that mean? What did we say that before? It means what? Not twisting, no? Okay, so what is that going to imply? It's going to imply that if we do the angle of twist of cell 1, it will be equal to 0, and if we do the angle of twist of the second cell, it should be equal to what? 0 as well. Okay, let me know what would be the only difference in this problem on how to solve it. If, for example, here on the page, I did not say that Vy was applied at the shear center. What would be the only difference? What would that be? Okay, this will not be equal to 0. They will be equal to each other. Yes? Because you will say that this cell will be formed the same as this one, no? Okay? But the procedure will be absolutely identical, no? It doesn't change anything. Yeah? Okay, so let me go to the next page. I have so many pages now. All right, so let me do a figure again. So let me first write down the equation. We have d theta dz, the general equation is 1 over 2a integral of q over gt ds. Okay, and we have, so this is the general equation. And what we have is, I'm just doing figures, you know, I like a lot of figures. So let's see on the figure, assume this to be equal here to Q1. Okay, so in this one, I'm going to start putting here the results that we had before. So help me a little bit over here. I don't know. Okay, maybe you can see the two figures. So we know here the shear is 0 over here on top, 0 over here, 0 over here, and 0 over here. But we need to find out what is on the side. So Q34 was equal to what? Negative, no? So we know that it should go actually, instead of going down, it should be going up, no? Yeah. And that value will be, the magnitude will be Vy over 1000. Q61 is positive, so we can leave this one positive. Vy over 1000. And Q25, we find out Q25 to be negative, so it needs to go up. And the value of this one will be, I don't know how to write it down, will be 2 Vy over 1000. I don't know if you can see it. Let me zoom a little bit over here for a second. Okay. Okay. All right, let me zoom out a little bit now. So now from this figure, we're going to find the angle of twist of cell 1. So let's say using figure. E theta easy out of first cell should be equal to what? Should be equal to 1 over 2 A1 GT, because every single cell is made of the same material, has the same wall thickness, no? Okay. All right, so the general expression would be, now we need to go around this Q ds. So in this case, Q are constant values. Yes? So the integral would just be Q times S. So this should be equal to what? 1 over 2 A1 GT times what? So there's different ways to do this, okay? But I'm doing it this way. Then if you want, we can discuss it other way. So let's see, Q1 over here. There's different ways to write it down. Q1 over here is going to go through what? It's going to go through what? S23, no? Plus S34 plus S45 plus S52. Yes? So it'll go through the whole cell, no? So this is going to produce an angle of twist of what? In the counterclockwise direction. Yeah. Now, this one over here, Q34, is going to make it to go clockwise or counterclockwise, the angle of twist? Clockwise. So that means it's positive or negative? Negative. So maybe let me write it down on general form. So we could write over here minus, and then we can put the value minus Q34, and then times the distance, no? S34. But what do you know about Q34? Q34 would be equal to what? is Vy over 1000, no? The magnitude. So you see why you need the figure. Okay, let's do the other one. What about Q25? Is going to be positive or negative? Positive plus Q25 times S52 if I use the same notation. And what would be Q25? Two Vy over 1000. Now, what else do I need to add? What is the shear flow that I'm missing? The Q2, no? Yes, it's going to go on this side, no? Yeah. So the Q2 is going to produce a positive or negative twist. This one. Anyone? I mean, this one is going on the opposite direction than Q25, no? Yeah, so it should be negative minus, you have done this before, Q2 times what? S52. And you close the parentheses. Okay, similarly, d theta dz of the second cell will be equal to what? 1 over 2 A2 GT. You go around cell 2. The 1 over 2 A2 GT. We do the same thing. Let's maybe follow the same order. In this case, now Q1 is going to produce a positive twist or negative twist. The one that's coming up here. This is cell 1, cell 2. Q1 will be producing what? Clockwise or counterclockwise? On this cell, we'll be going up, no? Q1. So we're creating clockwise, no? That one should be negative. So over here, minus Q1, which is going through what length? S52. So now let's look at the other one. So this is 0. This is 0. Let's look first at Q61. With Q61 producing a counterclockwise, I mean positive or negative? Positive. So let's say plus Q61 times S61. And what is Q61 is Vy over 1000. What about the Q25? Negative Q25 S52. We know Q25 is 2 Vy over 1000. And now maybe I'm going to put here the points here. What would be the last one that we need? Q2, perfect. We'll be going through what? We'll be going through all of them. So it's what? S12 plus S25 or 52 plus S56 plus S61. Okay, so I'm going to put right here solving the above two equations. I'll let you do it. Okay, the above two equations. You get that Q1 is equal to negative 1.3 10 to the negative 4 dy. And Q2 is equal to 2.17 10 to the negative minus 4 dy. Maybe I forgot to ask you something, which is pretty important. Okay. Why am I giving you all the results in function of Vy? Is that important or not? Why? Because when we do the deformation, we're gonna have to take the partial derivative in function of Vy, no? We need to find all the shear forces in function of Vy. Yeah? Okay. All right, so now that we have this, what can we do? We can just go back and say the Q, whatever, 1, 2 will be equal to the Q bar 1, 2 will be Q12 plus the Q2, no? Yeah? Okay, so let's see if I have some values here. Okay, so finally. So the shear flows are what? So will be, let's say the Q bar at J is equal to Q at J plus Q, either 1 or 2. Okay, I write down the general equation. Okay, so get ready here to copy. All right, so Q bar 1, 2 should be equal to 1, will just be equal to Q2. It was Q2, so it's equal to 2.17 10 to the negative 4 Vy. Q bar 2, 3 would just be equal to, I'm just going to put the values, negative 1.3 10 to the negative 4 Vy. Q bar 3, 4 would just be equal to negative 1.31, negative 1.13, sorry, negative 1.13 10 to the minus 3 Vy. Q bar 4, 5 will be equal to minus 1.3 10 to the minus 4 Vy. Q bar 5, 6 equal to 2.17 10 to the minus 4 Vy. Q bar 6, 1 equal to 1.22 10 to the negative 3 dy. And Q bar 2, 5 equal to 1.65 10 to the negative 3 dy. Okay, if you want, we can put here Q12, if you want, Q bar 2, 3, Q bar 3, 4, 2 bar 4, 5, 2 bar 5, 6, 2 bar 6. Okay, so now, again, I imagine you are using MATLAB or Maple for this, so substituting into the expression that we said this will be, let's say Q sub 2 will be equal to the integral 0 to L of Q sub I over GT partial of Q sub I partial Vy. I forgot here an integral sign. Yes times dz. So basically you see that put over here the bar, Q bar, actually it should be Q bar over here. So I'm just gonna write maybe the first two terms, but we do this equation, what should you have? You should have integral 0 to L, which is 2000. And now what will you have? Q bar 1, 2 divided by GT times partial derivative of Q bar 1, 2 with respect to Vy. So what would be that value? Will be the 2.17 10 to the minus 4 times the distance. What will be the value of the distance over here? As 1, 2. Okay, let me do another one, plus Q bar 2, 3 over GT partial Q bar 2, 3 S23 divided by Vy plus blah, 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 all the different values. Up to which one? Let's say this will be the last one, plus Q bar 25 over GT partial Q bar 25 over partial Y S25. At the end should be dz. So if you do this calculation, you get that Q sub 2 is equal to 13 dy over 23,000, no, 2,382,080. So 238,280. I mean, you see that here, I highly recommend to use MATLAB or Maple, no? Yeah? Okay. So the total deformation is, let's say, Q total will be equal to what? Q1 plus Q2. So I don't remember the expression for Q1. Oh, we didn't calculate it. So Q1 we had integral 0 to L dy over EI L minus Z square dz. And here we have plus 13 dy over 23,8280. So this is going to give you, let's see. Q1 will be equal to, if you do the calculation, 21.17 millimeters plus the one due to shear is 2.43 millimeters. So the total will be 23.59 millimeters. So again, this is the deformation due to bending. And this will be the deformation due to shear. Yeah, I'm the same way, I don't know what to say. I mean, basically, you see that conceptually these problems might not be difficult, but they involve a lot of calculation, and it's very easy to do mistakes, no? So I think I keep saying everybody that comes in my office, do not try to do this problem by hand. I mean, do the work by hand as we did, but do all the calculations using MATLAB, no? Okay, because if you do one mistake somewhere, you're going to carry that error all the way. So any question about what was the process? How to get to the answer? So basically now you're going to tell me, is it worth all the work to find the deformation due to shear? Personally, I think no. Okay. So why in this class we have been spending so much time about calculating shear, and more shear? Any guess? What is probably the most, I mean, let's say there's one component on the aircraft, one item that is repeated multiple times. What do you think it is? Rivets. Okay, exactly, rivets. Okay, so for example, to calculate the number of rivets that you need to put for each panel, how do you think you calculate it? By looking at the shear flow, no? So you know between this panel and this panel is that much shear, no? And let's say you know that each rivet can support a certain force, no? So if you multiply the shear force by the length, you have the total force that needs to be applied in that section. So you might know what is the minimum number of rivets that you need to have over there. Okay? And everything on an aircraft is made out of panels that are rivet either the fuselage or the wings, no? Okay? So if you want, I mean, we'll do that next time, but basically you see why shear is so important. So obviously, you have a lot more rivets than you need to have. Why? I mean, obviously for safety, but what is also something very important that is important for the panels to have on the wing? What is something that they spend a lot of time? Does the shape of the airfoil is important? So the shape of the panel is better not change, because then it's going to change the shape of the airfoil, no? Okay, so you need to make sure that that panel is well attached to it. Okay, so I'm just going to mention it. Probably that's what we do next time. But now a wing, as it's moving, then probably will be, when it's flying, it will bend a little bit up, no? And when it's on the ground, a little bit down. So what happened to the panel, let's say when it's flying, when the wing is flying, the panels that are on the top, are they in tension or compression? Compression. So what happened to something that is in compression? it buckles, no? Okay, so something important also to determine in the aircraft components to know what is the minimum load that will make the structure to buckle, so that you make your design to stay away from that load, no? Now I have a question for you, and this is what is difficult about buckling. Do you think buckling is a, how to say, a continuous problem, or is it a instability? Is it a stability or instability problem? So for example, do you think that if I push over here with my hands in, let's say I'm making up, okay, 1 Newton, is this going to buckle at 1 Newton? Let's say I do 2. Now here it cannot buckle, no? So it's going to buckle at 2. So it's either buckle or is not buckle, correct? So it is a stability problem. Okay, really what happens is that once you have the buckle and you keep pushing, then it's going to keep deflecting, no? But this is a different problem. But initially, the buckling problem is just a stability problem. It's either buckle, and something you cannot, for example, predict if the panel is completely flat, is it going to buckle up or is it going to buckle down? It could buckle in any direction, no? Okay, so I will give you some, basically some empirical equations, just that you have, and that's about it. There's not much more we can do, okay? If you look at the problem, it's pretty complicated. So that will be it for today. So I have 5 minutes to give you back the exam.